Recording. Then live stream. Live stream. You can hear. Yes. So welcome back, everyone. Now, again, I'll not list all the possible graph parameters that you can find using Sage, but again, the most familiar ones are already defined. So distances, diameter, radius, eccentricity, all of these are already there. Okay, so distance again, you need two parameters. So g dot distance. So let's say maybe C10. Yeah, we have defined C10, right? Let's say C10. C10 dot distance between 2 and 8. 4. As you can see, 1, 2, 3, 4. Okay. Similarly, C10 dot diameter. Diameter is 5. Okay. You can even ask for what is the complement of, what is the diameter of the complement of C10? Any idea? What can it be? Okay, what are the possible values? We should do a little bit of theory also. So, what are the possible values of the diameter of the complement? Can it also be 5? Yes. Anything, any theorem you know about diameter? Diameter? Theorem relating diameter of a graph and the diameter of the complement. If the diameter of the graph is greater than or equal to 3, the diameter of the complement is less than or equal to 3. So here the diameter of the graph is 5. So you expect that it should be 1, 2, or 3. Can it be 1? 1 diameter, 1 is only for complete graphs. Graph is complete if and only if it's diameter. So it should be 2 or 3, right? It is 2. Okay. The graph is disconnected, but not totally disconnected. Then the complement will have what diameter? 2, definitely, right? If a graph is disconnected, its diameter, the complement will have diameter 1 or 2. Again, 1 only if it's complete. That means the graph is totally disconnected. So if it's a non-trivial, means not totally disconnected, but disconnected graph, its complement will have definitely diameter 2. Okay. Of course, converse is not true. Here, graph is connected, complement is also connected, and so on. Okay, now, so we have seen families of graphs, path cycles, complete bipartite graph, and so on. Generalized Peterson graph is also there, by the way. Right? Generalized Peterson graph is there. So yeah, you need 2 arguments. Yes. Right. Anyway, now I want to discuss not families, but classes of graphs. So how to define some class of like graph from a class. So as I said, the problem is when you say a class of graphs is defined by a property, which need not completely specify the structure, right? Special cases it might. So if I say tree of order 2, there is only one connected graph of order 2, in fact, right? That's K2. So that is completely specified. But if I say tree of order 5, tree of order 10, it's not completely specified. So what you can do is, there are ways to create graphs in a random manner. Okay. So one of the most useful features of this is you have something called random graph. Okay. So you can see that there are several different random graphs here. Okay. So let's see the most basic one, which is random, one of the most basic ones, random GNM, which is not of any particular class. It is just a graph which is randomly generated with a specified n and m. Well, n and m, is just somewhat standard or conventional notation for order and size. So if I say random graph of order 10, say size 14. Okay, say call this G. We'll print first. As you can see, there's no need to print this at all. It actually gives you a randomly generated graph of order 10 and size 14. Okay, 10 vertices, 14 edges. Why is it randomly generated? Suppose I evaluate the same cell again. You can see that the graph has changed. Order and size, of course, remain the same because we specified them. The graph changes, right? To see if it has actually changed. Of course, it could give an isomorphic graph. It's not guaranteed to change, right? It's not like it will remember what it gave previously. Every time it's randomly generated, that's all. But you can make it print some other things so that you can see whether there is any change going on. So currently the degree sequence is this 5, then 6 threes, and then 2 to 1. No, 7 threes, I guess. 6 threes, correct. Yeah. So now it is different, right? When evaluated again, it is now 5, 4, 4, 3, 2, 2, 2. Yes, it can give disconnected graphs also. So here I've given 14 edges, so it's not too likely to be disconnected. But is there any chance at all that it can be disconnected? If you have 14 edges, yeah, it can be disconnected, right? Not, yes, here it is. So it understood that we were discussing disconnected graph and gave. By the way, some of these graphs might actually be disconnected and we are not seeing them correctly. That's the thing. Because in the drawing, the edges will cross. We have to really carefully see whether it's really connected or not. If you don't want to carefully see, then what is the other option? You can do this. Okay. Yeah, so this is again, but this is just an isolated vertex. Is there any other possibility other than isolated? Okay, let me decrease the number of edges. So then it's guaranteed, right? Almost like I will not make it guaranteed. I'll make it like 12 or let's say 11 edges. So if I give 9, then what is going to happen? It will either be a tree or it will be disconnected, right? Because if it's 9 edges and 10 vertices, so if number of edges is or the size is order -1, then it's connected if and only if it's a tree, right? So here it could be, yes, now it's disconnected, but again with just one isolated vertex. Again, so yeah, now you have 2 isolated vertices, then another component which is K2, then another connected component. So you have several components here, right? Can you even see that also? Sorry. Number of components you can see. No. Connected, yeah, sorry. It is, the full name is connected. We often call them components, but the full name is connected component. So if I say g dot connected components, it will give the list of lists of vertices of the different components. So this is, you can see a list of lists, because the first list is one connected component, all the vertices in one connect. Second list is this isolated vertex, which is another. Yeah, so here it will give, see, 0, 3, 5, 6, 7, 8, 9. That's one component. 1, 2, that's one component. 4, singleton 4. That's another. Most of these things that you can think of, which you obviously need, are already there. That's again the point I'm trying to make. Most of the things are already there. Eccentricity of not the graph, eccentricity of a vertex of a graph. So you just write, guess what it is. That's it. G dot eccentricity of whatever. Right. So in this case, what will be the eccentricity for the current graph? Yeah, if it's defined, it's infinity, or it's undefined, right? Infinity. Yeah. So it depends on your convention. Because if it is disconnected graph, maximum distance is either not defined or infinity as per your convention. Yeah, so if you take a connected graph, so there's some chance of, yeah, this is connected. Right? Yeah, the eccentricity of 9 is 3. Eccentricity of 0 is 4. Eccentricity of 4 maybe, yes, little larger, 5. Okay, again, since this is, each time I have to come back and edit the cell, which is a little slightly inconvenient. So one easy way to do this, when you want to repeatedly check different random graphs defined by some parameters, there is a nice way to do it. Let's start with something simpler. Suppose I want to look at different cycle graphs of different orders. Okay, cycle graphs of different orders. So what do I need for a cycle graph? I need the order. Let's say I specify the order, and then see. Then I show the graph and whatever parameters I need. So most of the parameters are obvious. Okay, let's say I want to check the diameter. So I'm just starting out with graph theory. I don't yet know what is the diameter of a cycle graph in general. I want to explore this, right? So I can do this, right? And I can change these values and check. Yes, Eulerian graph, I'll come to that as well. So the thing is, if I want to change the value, then I have to go back here, change the value, evaluate the cell again. What is an easier way to do this? That's what I want to do. So instead of writing it like this, there is an interact widget. Again, in maybe 1 or 2 out of these installations, this might not really work due to some errors in the system. Okay, but I hope most of you will get it. So interact, so the syntax is at the rate of interact. Okay, this begins the definition of what is called an interact widget. Now in this, you have to define a function. So function definition you saw in the previous session also, in the linear algebra session also. But the name of the function doesn't matter because we are not going to call it. So we'll just give a simple name which we will not use again, which is underscore. You can give any name you want. Actually, it doesn't matter. But it's common to give it underscore or underscore underscore or something because we are not going to call it. The interact widget will automatically use it. And then what parameters are we using here for defining this particular graph? Only one, n. So that n we will give here, okay, as a range. So minimum 3 you need. And let's say maximum I want to go up to 25. So I'll give in simple bracket parentheses, right? 3 dot dot 25. That it's syntax, okay? You don't give dot 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 or dot 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 dot. It is specifically dot dot, 2 dots, colon as for your function definition syntax. Now, whatever you defined before, here give the same thing, right? You can copy paste, but careful about the indentation. Sorry, not this. C equal to, sorry. Okay. Now I'll evaluate this. Now you see there is a slider here. I don't have to go back and edit the code. I can just drag the slider. So each time it will generate a new graph with that parameter, with that updated parameter value. And then whatever you asked for, it will show them. Right? So you can actually look at this. So in research, this is very simple thing, just basic graph theory. But when you are doing your research and you are studying a particular parameter, like so many graph indices are there, right? Like, Wiener index, Zagreb index, so many other graph parameters. And of course, spectral graph theory. So energy, different energies of graphs are there. So what you can do, what you can try to do is make this interact widget, generate a graph, either a particular class. So if you are only studying energy of cycles or Wiener index of cycle or whatever it is, generate that, print that value, change this value and see what you get. Another way is to use a loop and print the values for different things. But this is also, you can see the graph structure at the same time as seeing this. So if it's something more complicated, right? So seeing this, you can form a conjecture that, okay, this parameter is going to have such and such a value. And then you try to prove it. Okay, so that's like experimentally you're doing it. Experimental means finally you have to prove it theoretically, but experimentally you're discovering what is true, right? Theorems you're discovering experimentally. So here, if I'm going through this, then experimentally I will see that the diameter is what. So if I go to 3, getting diameter 1. For 3, I'm getting diameter 1. For 4, I'm getting for 3 and 4, I'm getting diameter. Yeah, 3 is 1. For 4, it is 2. For 5, it is again 2. For 6, it is 3. 7, it is again 3. Then 4, 4. 5, 5. 6, 6, and so on. So what is the guess? What is the guess for diameter of cycle of order n? N by 2? Floor of n by 2. Right. You know it. If you studied basic graph theory, you know that it's floor of n by 2. You can also theoretically prove this without much difficulty. But if you don't know it, if you're studying graph theory for the first time, you can explore and find out. And again, if you're doing research, you can do this with some more complicated parameter and you can find out what those parameters are. Yes, domination number. Domination number, yes, you can find like this. Connectivity, yes, connectivity also you can find like this. Okay. So dominating set. So this will give you a minimum dominating set if I'm correct. You have to check the documentation because so many aspects of graphs. I'm not familiar with all of them in Sage, right? I may know the definition, but not in Sage. So if I understand correctly, this will give you a minimum dominating set. Yeah. So it's cardinality, of course. This is basically a list. You can just use len function. That should give you the domination number. Otherwise, also, if it's a new index, like or not very old text index that you find in textbook, only in something that is defined in papers, then you can write the program for it. It's not difficult. So we'll also do some programming. Okay. Maybe in the next session, we'll do some programming so that we look at other more complicated parameters. But the basic thing here is interact widget. Now, again, coming back to this. Here we had a random graph, right? So how can I do this? Going back to this complicated example, a slightly more complicated example, I want to now make it interactive. So here there are two parameters, n and m. So again, I give a slider for n and for m. Don't forget indentation. You can repeat the same experiment as before, but now, yeah, no, my vertex set should not be non-empty according to my definition. So yeah, you can do the same experiment as before, but with more ease. Right. Yeah, obviously, if you ask for 23 edges in a 6 vertex graph, it's just going to give you the complete graph. Eccentric connectivity, I don't know this definition. So you'll have to tell me the definition, then maybe I can help you write the program for it. But again, that will be in the next 1 or 2 sessions. Okay. I may try to look it up and have it ready. Maybe we'll take it up in tomorrow's tutorial or something. Okay. Independent sets are also there. Yes. Independence number, independent sets you can find. Those are already there. And again, it's not too difficult to write codes for these. Right. So I also want to show you some other randomly generated graphs. So this is the one of the basic ones, which is random GNM, easiest to understand because you simply specify order and size. But another way to generate a graph randomly is random GNP. So N is again the same, but P stands for not order, because order is already N. P stands for probability. So if you give, let's say 0.4, then for every pair of vertices, it will add an edge with probability 0.4. Means it will try to add an edge. It will sample. Okay. So with 0.4 probability, it will add an edge. So because it's a randomly generated graph. So imagine if I give, suppose if I give a 0.5 as probability, then it's like you first draw 10 vertices, no edges. Now you ask for vertices 1 and 2. Flip a coin, fair coin. Heads, add edge. Otherwise, don't add. Vertex 1 and vertex 3. Coin, heads, add edge, tails, don't add edge, and so on. For all the pairs of vertices, it will do this. Yes, no edges will be added. Yes. Yes. So I'll always generate this one. And if I give 1, it will always give the complete graph. If I give anything in between, see so now, like earlier, if I do now when you do this repeatedly, so I'll keep n fixed for now. No, no. Yes, okay. Yeah, correct. So here, see, this is a bit the syntax you see. I didn't give 0.1 dot dot 1.0. That might also work. I'm not sure. No, that doesn't work. Yeah, so I have to give. So this is slightly different. This one where I'm specifying the step size for increasing. So 0.1 comma 0.2 dot dot 1.0. I can even give 1. This means that give me a slider with values from why didn't I give 0? 0 to 1, but changing it as 0, 0.1, 0.2, etc. So I'm specifying the pattern. To this extent, you can specify. Okay, what was your question? It might give error or it might just give consider it as 1. So either way, I cannot predict. Hmm? Yeah, I can try. So yeah, that is an error. Yes, it gives an error. So I can't predict because sometimes what it does is it just does it smartly. Okay. Takes the best possible interpretation. Yeah. So here, now if I change the probability, I get different graphs. You can see that even if I keep the probability same, so right now the probability is 0.3. If I again come back to 0.3, now there are 11 edges, whereas earlier there were 17 edges. So the size is now not fixed, unlike in GNM, where the order and size are both fixed. Here the order is fixed, but the size is not. The size can change even for the same probability. Size can change because it's random. The edges are added randomly. So theoretically, it is possible that even though you give probability say 0.9, you might get a totally disconnected graph. Of course, highly unlikely, right? You have to try a million times. Like you can calculate the probability. Suppose you give 10 edges and probability 0.9. What is the probability you get totally disconnected graph? 0.1 to the power of 45, right? 10C2. 10C2 edges are there, possibly. 10C2 pairs are there. Huh? Totally disconnected, not disconnected, totally disconnected. Disconnected, yeah. That's difficult to calculate. Here, see, all the probability is quite low, 0.3. Still, you are getting a connected graph actually. Disconnected is? How will you calculate? Because there are so many disconnected graphs. You may get like one complete graph on 8 vertices and then one isolated vertex, or like K2 and so many different possibilities. That's difficult to calculate. You can, but again difficult. Okay. Other. So far we have not seen trees at all. So if you want to generate a tree, again, because it's not a family but a class, you can only generate a random tree, right? Other than specific trees like star graph or path or something, you can generate a random tree. So how many parameters will you have to specify here? Order and size? Only order. Size is completely determined for a tree, right? If I see random tree of order 10, size is of course 9. There's no way to change that. Here it is. And now you can try that tree layout. So it will give a rooted tree layout. Okay. The current layout, what you see is spring only. If you give tree layout, it will actually give a kind of rooted tree layout. Yeah. The root here is chosen for some reason as 4. Then from that, there are 3 children. Then 8 has one child, which has one child, and so on. So it's always going to give you a rooted tree layout. Probably that root might actually be the center, is it? One of the central vertices. Center also, by the way, you can find. Yeah, it is one of the central vertices. So I don't remember. I don't know if always it chooses one of the central vertices. Most probably it does. Okay, that would make sense. It would choose. Yeah, I think the random. I mean, the tree layout. If you take, it will choose either there is a unique center or there are 2 vertices which are adjacent, right, in the center. So it will choose one of those central vertices and then give a root. That is the root, and then give the layout. So this is a randomly generated tree. Possibly, yeah. T. No, position you can set for any graph. Huh. Huh. Oh, okay. I have not tried that. Root. Yeah, yeah, you're right. You can set the root. I have not never seen this before. Yeah, so you can actually set the root manually if you. Yes. So that's also possible. Similarly, random bipartite graph. So here, random bipartite, how many parameters? Two parameters, just like complete bipartite. You specify the orders of the partite sets. Actually, we need to specify the size as well. Let me see. Yeah, yeah. You need to specify the probability also. Okay. For random bipartite, you also need to specify the probability. Yes. So, but it doesn't give you the nice layout. That's the only thing. Again, you can always ask for the partite sets. Wait, this is. So I should explain the labeling here. For bipartite graph, the default labeling is 0, comma I and 1, comma j. 0, comma I means vertices of the first partite set are labeled 0, 1, 0, 2, etc. And then vertices of the second partite set are labeled 1, 1, 1, 1, 2, 1, 3, etc. Okay. That is just the convention that Sage is following for bipartite graph labeling. Another place where you see this is if you take Cartesian product. So I think we'll also look at the basic graph operations before we'll stop in 5 minutes, right? 4:30. Yeah. So we'll just quickly look at some of the basic graph operations as well. So you can go home and explore all these things. So if you have two graphs, so now I have take two smaller graphs. Yeah, so inserting graph drawn in Sage into LaTeX document, as I discussed earlier, there are two ways to do this, at least. Which is one is you can save the image in whatever format you want, PDF or EPS recommended, and then insert that. Otherwise, you can use that LaTeX command, LaTeX function to get the TIX code of this and then copy paste the TIX code and modify it as per your need. Right. So these are the two options. So the advantage of the TIX code option is that you can customize the vertex appearance and so on. So right now it is plotted as some circles. By the way, vertex size also can be specified. I didn't show you earlier. You can make it look like dots, only that labels will be still shown inside. So if it's a very small dot, it will, like you can see here, it is trying to show it inside, but the size is too small, right? So if I specify, let's say 200, 200 is the default size, I guess. So it can make it bigger, right? You can also make it much smaller. So especially if you want the usual kind of. So this is an option. And then you can get the ticks code and then insert it in the LaTeX document. Right? And then modify it. You can manually position the labels and so on. Right? That's not a bad option. Okay, going back to graph operations. Let's take some small and simple graphs. Okay, these are your P4 and C5. Now, one of the basic graph operations, Cartesian product. Disjoint union is there, of course. Okay, we'll see that. This is not very interesting. So I'll just do that first and get it out of the way. So, yeah, that's the very, very basic operation where it's just union. No, nothing else. And yeah, what is another variant of this? Basically, disjoint union, but you do something with the edges. Join. So in the join, it's not easy to see here. It will take the disjoint union and make all vertices of the first graph adjacent to all vertices of the second graph. So that's a join. That's also there. Okay. But the other, sorry, I'll keep it there. Yeah, it's not very obvious, but I think you can kind of see here. So here is that P4. 0, 0, 0, 1, 0, 2, 0, 3. That's the P4. Then 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. That's a C5. You can see that in here. And then all vertices of P4 are made adjacent to all vertices of C5. But the other more interesting graph operation is the Cartesian product. So here, how many vertices should be there? If you have 4 vertices, if here and 5 vertices there, it should be 20 vertices. 4 times 5. And then the adjacencies are determined how? Say UV is adjacent to XY. If either U is equal to X and V is adjacent to Y, or U is adjacent to X and V is equal to Y, right? The more intuitive way of thinking of this is you take, so if you're doing P4 cross C5, say one way is you take 4 copies of C5. Okay, so replace each of these 4 vertices with 1 copy of C5. Think of it that way. And then whenever there is an edge here, they are also between the corresponding, between those 2 copies, make the corresponding vertices adjacent. So you have 1 copy of C5 here, let's say at the vertex 0, another copy at vertex 1. So then 0 of this copy is adjacent to 0 of this copy. 1 of this copy is adjacent to 1 of this copy and so on, right? So you have C5, 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 but together they form P4 in some manner, right? So that's what you can see here. This is, as you can see, this is the 0th copy. This is the first copy, second copy, third copy. Right? And then this 0 is adjacent to this, or this, yeah, 0, 0 vertex. So I'll make it more visible. All right. So you can actually see the vertex labels here. So you see 0, 0 is adjacent to 1, 0, which is adjacent to 2, 0, which is adjacent to 3, 0, right? Similarly, 0, 1 is adjacent to 1, 1, which is adjacent to 2, 1, which is adjacent to 3, 1, and so on, right? That's the Cartesian product. And again, it's actually symmetric. So you can also, instead of doing what I said earlier, you can take 5 copies of this P4 and then make the corresponding vertices adjacent cyclically, right? So you have 1 P4 here in vertex 0, 1 P4 here at vertex 1, and so on. Then 0 of this is adjacent to 1 of this, which is adjacent to sorry, 0 is of this is adjacent to 0 of this, which is adjacent to 0 of this, and so on. Right. Corona product, I think it is there. I'm not sure. What is another name for it? Oh, possibly it is not. Although it is an old definition, it's actually found in error if I'm not wrong. Anyway, it can be defined without too much difficulty. Okay, you take if you're doing graph of order n and graph of order n1 and n2, you take n2 copies of n1. Sorry, n1 copies of g2. Make all the vertices are adjacent to one particular vertex here. Yeah, can be done with simple programming. So again, we may see that as an example in tomorrow's session or something. Okay, we'll see. Yes, there is also the categorical product, also called Kronecker product. So, direct product means this only. Possibly both names are there. Not sure. Usually for graph, no. So this is categorical. Chronic. Yeah, Kronecker product means yes. Same. Because what this does is UV is adjacent to XY if and only if U is adjacent to X and V is adjacent to Y. So not that two equal other two adjacent, not like that. Both corresponding pairs should be adjacent. Then this will be adjacent. Okay. This is called Kronecker product because there is a Kronecker product of matrices, which you may discuss. So the adjacency matrix of the Kronecker product of G and H will be the Kronecker product of the adjacency matrices of G and H. So A of G Kronecker product H is equal to A of G Kronecker product A of H. That's why it's called Kronecker product, also called tensor product for the same reason, because it's also tensor product of matrices. And it's called categorical product because if you consider the category of graphs, this is the natural product, not the Cartesian product. And lexicographical and so on are there. So I think we'll stop for today. So explore the other options. Guess the names, see if they are there. Also, yeah, one thing I'll tell you before stopping. So if you're not sure about the syntax, so let's say you want to do, you just press dot, type dot and press tab, you will get so many options. But again, some of these options, you may not be sure what is to be given as a parameter, right? So let's say you explore some product like lexicographic product is there. It's easy to guess the syntax, but suppose you're not sure. You don't even know what lexicographic product is, right? So what you do is put question mark without bracket, right? Press enter. It will load the documentation. It may take 1 or 2 minutes. It will load the documentation there itself and show you. This window you can close here. Okay. So it will show you the syntax and basic example. Okay. So when you guess something and find out, you can just check the syntax if you're not sure what to do. Right. So explore and find out for tomorrow. That is your homework. Okay, we'll stop for today. Thank you.